We conclude with a brief discussion of the main points of this pre-lecture. First, Gauss's law can be used to actually calculate the spatial dependence of the electric field produced by sufficiently symmetric charge distributions. In particular, since we live in a three-spatially dimensioned world, there are three kinds of symmetric charge distributions, spherical, cylindrical, and planar, that produce fields that can be calculated directly from Gauss's law. Second, we used Gauss's law to demonstrate that any excess charge on a conductor must reside on its surface. We applied the same ideas to determine that a point charge placed at the center of a spherical shell conductor induces a charge on both the inner and outer surfaces in order to produce a zero electric field in the shell. We'll end this pre-lecture with a really big idea, namely the strong connection between symmetries and dimensions that underlies all of the specific calculations we did in this pre-lecture. We start with the observation that the field lines produced by spherically symmetric charge distributions expand fully into three dimensions. Their density increases as 1 over the surface area of a sphere, or 1 over r squared. If we squeeze the spherically symmetric charge distribution into a cylindrically symmetric distribution, the field lines become perpendicular to the axis and can expand only into 2 dimensions. Their density decreases as 1 over the surface area of a cylinder, or 1 over r. If we further squeeze the cylindrically symmetric charge distribution into a plane, the field lines become perpendicular to the plane but have no space to expand into. Consequently, their density remains constant, leading to a field that is constant over all space.